Lesson 4. Gradient, Energy. Section 4.3. Energy. Consider the work required to place a point charge q1 coulombs at point p1. If there is no other charge in space, the work is 0. If you move q2 coulombs toward q1 and place it at point p2, the work required is q2 times v21, where v21 is the potential at p2 due to q1. Furthermore, if you place q3 coulombs at p3, then the work required is q3 v31 plus q3 v32. The total work Wt is the sum of W1, W2, and W3. This represents the energy stored in the electric field due to the charge distribution. Now, let's bring in the point charges in reverse order. The first one is q3, for which W3 is 0. The second one is q2. W2 equals q2 v23. The last one is q1. W1 equals q1 v12 plus q1 v13. The total work is given by this equation. These are the total work amounts for the two different orders. The final states are the same regardless of the order in which the point charges are brought into the space. Thus, the total work amounts should be equal. The sum of these two amounts is twice the energy stored. This term is the work done against the fields of q2 and q3. Therefore, it is q1 v1. The same applies to the second and third terms. Thus, this is the energy stored in the field. Suppose that in a given volume VOL, charge is distributed with a density ρ coulombs per cubic meters. The summation of work for each differential charge ρ dV turns into a volume integral over the region VOL. This represents the energy stored in the electric field due to this charge distribution. Exercise 4.3.1. Pause the video, and answer the problem. Find the total energy Wt stored in the spherical volume. The answer to exercise 4.3.1. Pause the video, and check the answer. Exercise 4.3.2. This is your homework. Pause the video, and answer the problem. The remainder of this video is for your advanced study. The energy dW, stored in a differential volume dV in electric field E, can be expressed by this equation. The proof is left for future study. In exercise 2.3.1, the electric field intensity E was derived for both the inside and outside cases, as shown in these equations. The total work Wt is obtained by integrating the differential energy dW, both inside and outside the volume. This is the electric field intensity inside the volume. Then, this is the integral of energy inside the volume. The integration range is from 0 to A. This is the electric field intensity outside the volume. This is the integral of energy outside the volume. The integration range is from A to infinity. The integration is executed. The result coincides with the result in exercise 4.3.1. Here is a question for you. In the case of integrating ρV, the integration range is limited to inside the volume. In the case of integrating epsilon E squared, the integration range is both inside and outside the volume. These results coincide. Why do these results coincide? Here is a brief summary. In this lesson, we learned about the gradient. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.